Hello students, I welcome you all to this session. I am Vishali Kikan, Assistant Professor Electronics and Communication Engineering Department at KIET Group of Institutions. Today in this session we will be talking about the dopants and the diffusion furnace. So first of all we will be talking about the properties for designing and laying out our ICs. Then we will be talking about the dopants in general and in their characteristics. Then we will be talking about the dopants in VLSI technology. Then we will be talking about the diffusion system and the furnace. Okay, so first of all, the dopants and their characteristics. So boron and phosphorus are the basic dopants of most of the integrated circuits. Arsenic and antimony, which are highly soluble in silicon and diffuse slowly, are used before epitaxial processing or as the second diffusion. We will be having some kind of second diffusion as well. I will be talking about it later. Gold and silver diffuses rapidly. They act as recombination centers and thus reduces carrier lifetime. Boron is almost an exclusive choice as an acceptor impurity in silicon. Now why? Since other p-type of impurities have the limitations as follows. The gallium has relatively large diffusion coefficient in silicon dioxide, and the usual oxide window opening technique for locating diffusion would be inoperative. Indium is of little interest because of its high acceptor level of 0.16 electron volt compared with the 0.01 electron volt for boron. So this is the reason boron is an exclusive choice for p-type impurities, which indicates that not all such acceptors would be ionized at the room temperature to produce a hole. So aluminium reacts strongly with any oxygen. It's have higher reactivity than silicon or germanium. Then it will be forming aluminium oxide. If I have some oxide on the silicon layer, aluminium will be reacting with it. So if I have oxygen that is present on the silicon lattice, aluminium will be reacting with it and it will be forming aluminium oxides. So this is why aluminium is also not very useful. Now in the case of n-type dopants, the choice of a particular n-type dopants is not so limited as for p-type material. In p-type material our choice was highly restricted. The n-type impurities such as phosphorus, antimony and arsenic can be used at different stages of IC processing. The diffusion constant of phosphorus is much greater than for lead and AS, being comparable to that for boron, which leads to the economies resulting from shorter diffusion time. Okay, then the common dopant used in the VLSI fabrication are boron, phosphorus and arsenic. We have already talked about most of the dopants in n-type and p-type. Now in VLSI technology we have boron, phosphorus and arsenic, which are mostly used. Phosphorus is useful not only as an emitter and base dopant but also for gathering and fast diffusing metallic contaminants such as copper and AN, which causes junction leakage current problem. So it will be resolving our leakage current problem as well. Thus phosphorus is indispensable in the VLSI technology. We have to use phosphorus in the VLSI technology. However, NPN transistors made with arsenic diffused emitters have better low current gain characteristics and better control of narrow base width than those made with phosphorus diffused emitters. So I hope now you understood. Therefore, in VLSI, the use of phosphorus as an active dopant in small shallow junction and low temperature processing will be limited to its use as the base dopant of PNP device and as the gathering agent to remove the leakage current. Arsenic is the most frequently used dopant for the source and drain regions in the N-channel MOSFET. Now we will be talking about the diffusion system. How with the help of diffusion system we can make our atoms or the impurities go inside the semiconductor. The method of impurity delivery to the wafer is determined by the nature of impurity source. Two-step diffusion is widely used technique. In the two-step diffusion, first we will be creating the base in the collector, then we will be creating the emitter in the collector. So this is the two-step diffusion process to form the BJT. Using this technique, the impurity concentration and profile can be carefully controlled. The type of impurity distribution is determined by the choice of operating condition. Okay, I have already talked about the error function or the Gaussian diffusions in the previous videos. The two-step diffusion consists of deposition step and drive-in step. We have talked about in the Gaussian diffusion that how we have two steps, the deposition step and the drive-in step. In the deposition, we will just deposit the impurity on the surface. In the drive-in, the impurity will be penetrating inside the substrate with the help of the diffusion process. In the former step, a constant source of diffusion is carried out for a shorter time, usually at relatively low temperature, say 1000 degrees Celsius. In the later step, the impurity supply is shut off and the existing dopant is allowed to diffuse into the body of the semiconductor, which is now held at a different temperature, say 1200 degrees Celsius in an oxidizing atmosphere. The oxide layer, which forms entire surface of the wafer during this step, prevents the further impurities from entering or those already deposited from diffusing out. The final impurity profile is a function of diffusion conditions such as temperature, time, diffusion coefficient for each step. We have talked about all of these things. We have talked about a lot of other parameters as well, like the cleanliness parameter also. So then we have diffusion furnace. For various type of diffusion and also for the oxidation processes, a resistance heated tube furnace is usually used. Why a resistance heated tube is used? Because we will be having the very high and controlled temperature. We require very controlled temperature for our diffusion process. A tube furnace has a long hollow opening into which a quartz tube about 100 to 150 mm in diameter is placed. So here you can see this is my quartz tube and this is my full tube furnace. This is a horizontal tube furnace and this is my quartz tube. Okay, so we will be supplying a very high temperature, controlled temperature, which is around 1200 degrees Celsius, and we will be having the controlled temperature at the deposition step as well, which is 1000 degrees Celsius. So we have to control at two temperatures, so our furnace must be designed accordingly. Then we have the diffusion furnace. The temperature of furnace is kept around 1000 degrees Celsius. The temperature within the quartz furnace tube can be controlled very accurately such that a temperature within 1 to 2 degrees Celsius of the set point temperature can be maintained uniformly over a hot zone about 1 meter in length. This is achieved by 3 individually controlled adjacent resistance elements. The silicon wafers to be processed are stacked up vertically into the slots in a quartz carrier or boat and inserted into the furnace tube. So this is the example of the furnace tube. We will be having the sources. We will be talking about the different type of furnace when we will be talking about solid, liquid and gaseous sources. So this is the furnace in the case of liquid sources. So now here I will be concluding my session. I hope you understood each and everything. If you still have any doubt, you can reach out to me. I hope you will be joining me in the next session really soon. Thank you.